we're going to discuss triangulations. And triangulations will explain to us why every compact connected surface is combinatorial. So this is the question that we have. So is it true? Well, let's just say what a combinatorial surface is. So X is a combinatorial surface if there is a proper labeling scheme so that the quotient space that you get out of that proper labeling scheme is X. So X can be obtained by taking some kind of coloring code, which is represented by your word, then taking a disk and gluing its edges along by that code, and you get a two-dimensional manifold out of it, which is connected, it's compact, and we call that a combinatorial surface because the surface is described in a combinatorial sort of a way. And the question, this is sort of like the question we really want to ask, this is like the big question, is every connected, compact, well, yeah, that's what X is, a combinatorial surface, is every compact connected surface, and a surface is a two-dimensional manifold. So surface, this is just a two-dimensional manifold. Is it combinatorial? Does it arise in this kind of, with this kind of combinatorial type of structure? This is really what we ultimately care about, because even though it's nice that combinatorial surfaces can be classified in such a way, we want to be a lot more general. We want to be able to apply this to manifolds. It's manifolds that we care about. In general, when you have a topological space X, it can be a very abstract space. You do not necessarily know much about it. And a combinatorial surface is a very special type of space. It comes from taking a polygon in the plane and gluing its edges together. That's a very special structure you're putting on it. Whereas a manifold is a very general type of object. There's not much, you're not really assuming much about a manifold. And so you can ask the question, is it true that with these assumptions that X can be obtained in this combinatorial sort of a way? And the answer is yes. And I want to give you, sort of have a discussion about this so you get to see why that is, instead of writing a formal proof, which would be way too long, way too long. And it'll be more beneficial to at least say what the idea is, so you at least understand what causes to be true. And in order to understand this, we need to discuss triangulations. So triangulations is going to play a role here. So let's say what a triangulation is. Now, the idea of a triangulation, so intuitively, a triangulation is breaking up a space into small triangles that fit together nicely. Triangulations are actually used in graphics, computer visualization. We use triangulations. A computer does not actually draw a curve. It just draws lines, and it draws polygons, lines, polygons, polyhedrons, things like that. And it just puts them together with straight lines. And if you have a lot of them, you can create this illusion that you have this nice smooth surface that is curved and all of that. But in actuality, it's just made out of these small little line segments that are put together in a nice way. So for instance, if you look at a circle, I mean, even though on my screen it might look like a nice smooth curve, but in actuality, what a computer is doing is that, well, sometimes when you zoom in enough times, you can actually see it. But basically what happens is you sort of have a lot of points and then you have like these various triangles or something that fit together in a way, and it's drawing triangles. It's the triangles that are being drawn. It's only drawing straight lines. But you can see that if you have a lot of them, if you have hundreds of thousands of them, then what you actually see on the screen starts to resemble the object that you're actually interested in. So let's define, in rigorous terms, what is a triangulation. Now, triangle, this is a little bit confusing because if we're doing topology, then there really is no such thing as a triangle because there's no such thing as like a straight line or an angle in topology. So the way we're going to define a triangle, this is going to be a topological triangle, is we're going to take a Euclidean triangle, something that we can understand normally, and we're going to map it homeomorphically into our space. So here's the way the definition goes. Here's a definition. Let X be a space. And let's denote delta to be the following set in Euclidean space. So these are going to be points, let's say x1, x2 in Euclidean space with the property that, so what you want to realize about this is we want to define what a triangle is, or we want to get something that resembles a triangle in an abstract topological space. But when you're doing topology, things do not necessarily look like anything. So the idea here is to reduce everything back to the Euclidean plane where we understand what a triangle is, where we can see a triangle and all that stuff. So we define delta to be the set of points where, let's say, x1 plus x2 is less than or equal to 1, and x1 is non-negative, and x2 is non-negative. So as a picture, if you want to see this as a picture, it looks like this. So that would be delta. So delta represents this region, and it's a closed region inside R2. This is a line. So if you set x1 plus x2 is equal to 1, this is the line. Then you put the conditions that x1 and x2 are now negative, so you include these sides. And because these are weak inequalities, so they are less than or equal to, you get a closed region. So this is something you can actually see as a triangle. Now, how do you get a triangle in a topological space? Well, the way you get a triangle is by using a homeomorphism. So let X be a space. We denote delta to be this. So a triangulation of X is a collection of continuous maps. So we're not even going to say they're continuous. Maybe we should just call them, doesn't matter what you call them, phi I, that map this delta into X. So we're always going to be mapping the same triangle because topologically speaking, they're all going to be the same. So you make it bigger, you make it smaller, it does not really matter. We just pick a triangle. This one's convenient to choose because its equations, well, I should say its inequalities are fairly easy to write out. So you just pick some triangle. So this is the triangle, and then you map that triangle into your space. Okay, so that's your space. And so this is for, let's say I is equal to 1, 2, up to n. Okay, so you have n mappings of this Euclidean triangle into your topological space. And what properties are satisfied? So the first property is satisfied is phi I maps delta homeomorphically onto a closed subset of X. So let's call it Ti. So T for triangle. So this is the triangle number I. Now it does not actually have to look like a triangle, just to give you a picture. So here's a picture. So here's that Euclidean triangle, and you can map it into this. So you can easily imagine that this side gets mapped to that, and that this side gets mapped to that, and that side gets mapped to that. So then you have a triangle. I mean, and once you have a triangle, these are going to be your vertices, right? Because they're coming from those. So this over here is your mapping phi. This is delta. This is X. Well, maybe I should say this is a subset of X that's contained, and the image of that is called T. That's the triangle that's sitting inside X. And now we know what a vertex is, right? We would say that this is the vertex. Here, what it means to be a vertex, you would never say that this is a vertex. You would say there's no vertex. So that's what we mean, that the homeomorphism determines the triangle. So it might look very strange, but that's the way you do it. So the three vertices get mapped here, and the three edges get mapped here, and then this inside is what you call the face of the triangle. So this would be a triangle. So it's a very strange type of triangle, but that's what it is. And then, of course, you can have more abstract spaces that you might not even be able to visualize at all. But that's what we're saying. That phi, so the requirement is these are homeomorphisms. These are not necessarily homeomorphisms into your space X, but they're homeomorphisms to a closed subset of X. By the way, small comment, if X happens to be a Hausdorff space, then this image has to be a closed subset. The reason for this is actually quite simple. This is a compact set, so its image is a compact subset of X, and if X is Hausdorff, which is the kind of spaces we're working with anyway, its image will automatically be a closed subset of X. So Ti is just the triangle. So the difference is that phi, so phi, that is the mapping of the Euclidean triangle, and Ti is the corresponding abstract triangle that's sitting inside X. The next condition is Ti and Tj are either disjoint. Well, maybe before I say that, maybe I should say that X is a union of all of these triangles. So that should make sense because this is a triangulation. We're covering the space using closed sets. So in particular, it would mean that X is compact because it's a finite union of compact sets. The images are compact. Okay, so, and then the other condition here would be that, so the other condition would be that each Ti and Tj, so this is for I not equal to j, so if you take two different triangles, so here, these are referring to the images of this in your space, are either disjoint, they intersect in a common vertex, or they intersect in a common edge. So let me explain to you what I mean. So going back to our picture again, so we have phi. Let's say it maps this to this again. So these three are being mapped to, like, this is your triangle. It's a very strange looking triangle, but that's your triangle. And then you have another one, let's call this phi prime, and it maps it to, it could map it to something that looks like this. It's kind of messed up over here, maybe like this. So these are like the three sides being mapped to those three sides. If you look at the intersection, notice how they intersect. So that's the intersection. So now if you look, if you pull back, now you see it does not exactly make sense to say that they intersect in an edge because that's a Euclidean concept. A vertex and an edge, that's a Euclidean notion. It does not make sense topologically. So you have to use these maps to understand what you're saying. There's this intersection that takes place. So you have to interpret the intersection using this mapping. So this piece of the intersection, it corresponds, you see, it would correspond to, let's say, this side of the Euclidean triangle. And that side of the Euclidean triangle is an edge. It's an edge. And this over here, that is also some kind of edge. I mean, it does not have to be on the same, like it could be down here. It does not really matter. But the point is that if you find the corresponding region in the Euclidean triangle, it has to be an edge of that Euclidean triangle. So that's what we're saying. So to draw some more pictures is, so to keep the pictures a little bit simpler, you're saying you can have this situation, that's okay. You can have this situation, you see they intersect at a vertex. You can also have this situation where they kind of line up in a nice way. This would be fine. Whereas the idea is that you want to avoid something like this because they intersect, but that's not an edge. That's a piece of an edge. Or you want to avoid something like this. right? That's also no good. You want them to fit together in a nice kind of a way. So if you have two triangles, and these are topological triangles, they either are disjoint. If they intersect in a common vertex. Now again, vertex of a triangle, that's a Euclidean notion. So you really have to interpret that by using those homeomorphisms. You find the point in here, you find the point in there, and then you map that point back to the Euclidean triangle, and you map this point back to the Euclidean triangle. So if the corresponding points on this Euclidean triangle that we drew are actual vertices, then that's good. Okay, so that's what it means to be a triangulation. So let me give you an example of a triangulation. Let's talk about the triangulation of a torus. So as we know, the torus can be described with this gluing scheme. So we have A, B, A inverse, B inverse. So let's call this perhaps X. Well, maybe we can call this, let's call this D2 for the two-dimensional disk. And then we have the quotient map. This is the projection map pi into the quotient, and this is X mod tilde. I'm sorry, X is equal to D2 mod tilde. So you're going to take, I wrote a disk, maybe I should have just said a square. Maybe I should have written it like this. Yeah, I cross I mod tilde. So you have this space, you have these four sides. You're going to put an equivalence relation on its four sides with this kind of procedure that tells you the equivalence relation. And now with the equivalence relation, you can define a quotient, and then X is the quotient of that. And this is your mapping. So you get some kind of space out of it, and that space is what we call a torus. So let me show you how you can get a triangulation of your torus. So to get a triangulation of the torus, you need to, so basically what you need to do is you need to define a collection of maps from delta into X. Right? You need a collection of mappings that map a Euclidean triangle into X. If you actually look at X as a set, it's just equivalence classes of sets. Fairly complicated. But you want to be able to find nice Euclidean triangles that map nicely into X. So here's the way you can do it. We're going to first use this picture, and then after we draw the triangles over here, we can apply pi to it and map those triangles into X. So here's how we do it. So first of all, I want to just show you something that is not a triangulation. So if you look at this picture, notice we have two triangles. We have an upper triangle, and we have a lower triangle. The problem is that this lower triangle is not being mapped homeomorphically into X, because this point and this point and that point, they all get identified to a single point. So pi, when you take pi and you restrict it to this closed subset, it is not going to be mapped homeomorphically onto a closed subset of X. So that's not good. The vertices actually have to be distinct. So the correct way to do it is you're going to break up, you actually have to break it up like this. You have to break it up in this kind of a way. Break it up like this. And then you can introduce triangles like that. So if you do it like this, then you actually get a triangulation, because let's just pick one of these triangles. So if you take like one of these triangles right here, okay, notice that this point, it's being identified with these four corner points. It's not being identified with these two. Furthermore, this point on the upper edge, the points on the upper edge are not identified with the points on the left edge. So they're being mapped to distinct points. And this is also mapped to something distinct. So this would mean that this entire triangle, when you apply pi to that triangle, it is going to be mapped homeomorphically to a triangle over there. And then you can do it with a different triangle. By the same reasoning, you can also apply pi to this triangle, right? It will be mapped to another triangle. So maybe what I can do is, now, so there's a small little annoyance in the definition. We have a Euclidean triangle of a very special form, and that's a little bit different. But that's a minor annoyance. It's exactly when we talk about loops, and we always rescale it from 0 to 1. So this is the way we're going to define our maps. I'm not actually going to write down their equations, because the equations is not what matters. It's the idea behind it. So you're going to have triangle delta. So this is the So this is delta. This is the Euclidean triangle from 0, 0, 1, 0, 0, 1. That's the Euclidean triangle. You're going to map it. You're going to map it to this piece. You're going to call this mapping, for lack of a better name, let's say you call this mapping Fi. Well, let's just call it F. Okay, let's just call it F. What is F? So F is an affine map. So it's basically like a linear map. Not quite. It's a linear map plus a constant, which which maps delta. Maybe we can even say rescales, like rescales and translates, and also rotates and all of that into the required triangle. You see, we're trying to obtain a mapping of a Euclidean triangle into our abstract space. So we do it in two steps. We first map this to this piece. Okay, so this is actually something that's Euclidean because this is I cross I, and then you compose it with pi. So then phi would just be F composed with pi. That's what it would be. It would be F composed with pi. So you go with F. You first map this Euclidean triangle. Let's call this the standard Euclidean triangle. You map this standard Euclidean triangle into this rescaled Euclidean triangle, and then you compose it with pi. And pi, as we observed, would be a homeomorphism on this closed subset, and it will get mapped somewhere over here. And then you do this for each of the little triangles that makes this up, right? So that would be the idea. So then you go ahead and you do this for each of the triangles that makes this up. So you do it with this one, you do it with this one, you do it with this one. So you do it for all of them. So you always compose with pi, restricted to that smaller subset. And every time you use F, you use a different rescaling. But the point is, it is possible to construct mappings from delta into this space X that will satisfy the property that you want. So now, if you have two triangles in X, Ti and Tj, and I'm going to call these triangles in quotation marks because you cannot necessarily see them anymore, because X is now a more abstract space. It consists of equivalence classes. So you cannot necessarily see the triangles anymore. But the point is, each of these triangles, they came from triangles over here. Now, if it happened that a triangle Ti came from this one, it was the mapping of this one, and triangle Tj was the mapping of this one, then those are disjoint, and then there's nothing to check. But it could happen that maybe, then it could happen that it came from this one. Okay, and then you can see that this point, this corner point over here, like, what's the intersection between these two? The intersection between these two, that's the point of intersection. So what point does that correspond to on the standard Euclidean triangle? There it is. Is that a vertex? That's a vertex. And the same thing for this one. That corner point will correspond to that corner point of the standard Euclidean triangle. So what it means to be a vertex and an edge is not interpreted in the space. That would not make sense. It is rather interpreted by the use of these mappings, because those mappings sort of map a picture that you can see into a space that you cannot necessarily see. And then you use your standard Euclidean space to then interpret what it means to be a vertex and edge and all of that. So that's a triangulation of a torus. And there's other triangulations. Another thing you can do is you can cut this up even more. So if you wanted to, you can probably cut it up like this. So the point is, there's lots of different triangulations that you can use. So that would be a triangulation of the torus. Okay, so, and as an exercise, so I noticed that the screen got disconnected, so let me put the screen back up. Yeah, so the screen got disconnected, so give me just a moment to turn the screen back on. So that would be the triangulation for a torus, and as an exercise, you can do a triangulation for a projective plane and other surfaces that we've talked about. So the main theorem, so this is the main theorem, and this is a theorem that goes back to Radeau, and this is from, I think, the 1920s. That's from a long time ago. It's 100 years ago. So it's a theorem from the 1920s. So this is what it says. It says that if X is a compact, connected, two-dimensional manifold, then X has a triangulation. A triangulation will exist. And the proof of this, let me say this, it's very hard. In fact, I'm going to say this. I'm going to say that I do not think, well, I have never seen a proof of this. I have seen a lot of books say that there is a proof, but they never write the proof. So that's how difficult this proof is. They say there is a proof, but they never write it. Now, what Moncrief does, Moncrief says something very interesting. Moncrief says, the proof of this is not difficult, but it's very long. That's what Moncrief says, and he does not write it. But I disagree with that statement. It's very difficult because I've never seen books give a proof of this. Like you open up book after book after book, and none of them prove the theorem. There's only 2 books that I know that prove this theorem. So there's a proof in 2 books. One of them is Alfors. Alfors. This is the book we mentioned before, Riemann surfaces. So Ars Alfors gives a proof. And when I did not learn his proof, so I'm not familiar with this proof. But briefly looking at his proof, it appears his proof is actually rigorous. There are some books that I look at that sort of talk about this a little bit, but I would not say that their proof is convincing. It's just a lot of pictures, but at the end, it does not look like it is presented in a rigorous way. So Alfors appears to be one place where there is a rigorous explanation, and there's another book that you can look at. I've looked at it, but I did not learn the proof. It's by Moyes, I think Moyes. I'm not sure if I'm pronouncing his name. Now, Moyes was actually Moncrief's PhD advisor. So when Moncrief got his PhD, his advisor that he got it under was Moyes. So there's a book by Moyes, and it's called Geometric Topology in Dimensions 2 and 3. That's the name of the book. So geometric topology, I'm going to guess by geometric topology he means manifolds. That's my guess. So the topology of manifolds in dimensions 2 and 3. So surfaces in 3-dimensional manifolds. And what Moyes proved in the 1970s, he proved the more difficult version. So Moyes proved that if X is a compact connected 3-dimensional manifold, then it also has a triangulation. Though the meaning of a triangulation has to be changed a little bit, because you're no longer mapping triangles, Euclidean triangles. You're actually mapping Euclidean tetrahedron into your space, but it's a similar sort of idea. So Moyes was able to prove that in the 1970s. And he has this book, and I believe he proves that your space has a triangulation, even if it's a 3-dimensional manifold, and it's somewhere in the book. So I would say that maybe this is the best place to look at, because this seems to be the world expert. He's not alive anymore, but that seems to be who used to be the world expert on triangulations. And he also, somewhere in the book, discusses why 2-dimensional manifolds have a triangulation. And I briefly sort of skimmed through his proof, and by just looking at it, there's no pictures in it. He kind of seems to define things in a nice, rigorous way. So that's probably where you can look at. And it takes a while for him to prove it. I think he proves it at like page 60 or 70. So that would mean you would have to read like 60, 70 pages in a difficult math book. Think about putting all those hours trying to figure that out to get to this result that X has a triangulation. And all of the hypotheses of a manifold are actually being used. If you recall, one of the hypotheses of a manifold is that it has a countable basis. So you can form like a sequence of open sets, which allow you to determine that something is open if and only if it contains those open sets. So he actually uses that fact within the proof. So I was able to see, at least briefly, that the proof of that does take advantage of the fact that you have a countable basis. All of those things are being used. So we will not prove this. Like I said, I've never even seen a proof of this myself, because every book I come across, everyone says that it's either easy or it's well known, but they never prove it themselves. And when I've seen people talk about this theorem, they just assert it. They say it could be shown, but no one ever shows it. So perhaps this is like maybe an interesting research project, possibly, to try to figure out this proof and figure out if there's a way to greatly simplify it. And maybe if there's a way to do it, people will find it beneficial. But I've just seen that people constantly reference this theorem, but no one really proves it or talks about it. People sort of stay away from it. So this is the theorem which is responsible for the fact that every compact connected two-dimensional manifold has a polyhedral, well, I should say a polygonal representation by gluing sides of a polygon. So we're going to see how that follows from it. But this is sort of like the key theorem that explains why this works. So as I mentioned, so let's just say this. So we can mention that Moyes, this is the 1970s. So this is also true for three-dimensional manifolds. Okay, but it is not true for four-dimensional manifolds. So things, unfortunately, fall apart by the time you get to three-dimensional manifolds. So as we mentioned, the Poincare conjecture was proved, and that's the problem about three-dimensional manifolds. And it's a compact connected three-dimensional manifold whose fundamental group is trivial, and you want to show it's a sphere. So I wonder, I've not learned the proof of the Poincare conjecture, but I just wonder if Perelman, who proved it, whether or not he used the triangulation theorem for three-dimensional manifolds somewhere along in the proof. Because by knowing it has a triangulation, it means you can reduce your problem to a combinatorial nature, and then it becomes a little bit more manageable to solve. So this is why people think that there could be a classification theorem for compact connected three-dimensional manifolds. They can be triangulated. That's number one. And then number two, the Poincare conjecture was sort of like the key first step in classification. So we have that true. And then maybe in the future, people will figure out some classification theorems that will maybe give you a full list of all spaces that are three-dimensional manifolds, possibly, maybe. That's the hope. But for four-dimensional manifolds, people are not, that's not a solvable problem, because you cannot put a triangulation on them, and then it would therefore mean you approach the problem of four-dimensional manifolds like you did the two-dimensional version and the three-dimensional version. So if you've noticed, the way we classify two-dimensional manifolds is we used a polyhedral representation, and then we saw that you can kind of use copy and paste algorithm to put it into one of the standard forms, and those standard forms are your different kinds of cases that you can have. So that's sort of the hope that you can do for three-dimensional manifolds as well. But people are still working on that, from what I know. So instead of proving this theorem, instead, what we're going to do is I'm going to illustrate to you how this triangulation theorem can be used to create a polygonal representation. So let's do this. So let us accept the triangulation theorem and illustrate how it can be used to describe your space as a polygonal representation that we've been doing previously. Now, just a small comment. So if, let's say, T1, T2, up to Tn are triangles in your space X. So, of course, when we say triangles, we cannot visualize these triangles. More appropriately, what we understand is these triangles come from some mapping of the standard Euclidean triangle into X, and that when you restrict it, well, and that the image, the push forward, is Ti, and Phi is a homeomorphism between delta and Ti. So when we say they're triangles, we do not actually mean they're triangles the way you think of them. It's like in the previous example with a torus, like, what is a triangle? It's like a collection of equivalence classes of points. I mean, that does not look like any triangle, but what we understand is that there's a mapping of the Euclidean triangle, and then we therefore visualize the triangles by using the delta. That's kind of what we do. Okay, so the small comment here is, if you have triangles, then every edge of every triangle is shared between exactly two triangles. So to give you a picture of a triangulation, so here's a triangulation. Notice this edge. Notice how this edge, it's an edge between this triangle and that triangle. And that's what we're saying, that when you have your triangulations in your space, you have your triangles in your space, then the edges that are part of your triangulation. So again, an edge is not something you can see. You have a mapping of the Euclidean triangle into TI, and one of these three sides, right, one of these three edges, it corresponds to a region, and those corresponding regions is what you call the edges. So those are just the corresponding map regions of the Euclidean triangles. So the edges, so again, edges in quotation marks, that if you have an edge, there's exactly two triangles in this list that intersect together at that edge. And the basic reason for this, because otherwise it will fail to be a manifold. So we're assuming X is a two-dimensional manifold. It will fail to be a manifold because if you have, well, first of all, I mean, I know it's not a proof, but I do not want to give a proof of this. I just want to state this. So if you only have one edge and nothing else, then if you pick a point on the edge and you draw a little disk around it, notice that's not homeomorphic to R2 because you're including this boundary there. So that's not good. That's not an open disk. You want it to be an open disk, which is homeomorphic to R2. And that's why you need a second one to sort of close it off. So that's why there's exactly two. So what we will do is, so I'm going to give you an example. So here is an example of how you take a triangulation and convert it into a polygonal representation. But here's the way you do it. So instead of giving you a proof, because that would also be tedious, though I would say the proof of the fact that you get a polygon out of that, that is actually easier to prove. That's a lot more straightforward to prove. When you look at this example that we're going to do an example carefully, and then you'll see how it works. So it's not going to be anything deep. So, so I have this example. Now, this is an example that I took from a book by Massey. I think it's called An Introduction to Algebraic Topology. It's a good book. It's well written. It's a GTM book. And this is chapter 1. That's actually a good chapter in the book. The first chapter of his book begins by discussing two-dimensional manifolds. And Massey, just like all of the other books, he never proves the triangulation theorem. He just says it could be shown, right? It could be shown. But he does nicely explain, so he does something that other people do not do. He does nicely explain how you can use a triangulation to get the polygon. So he does nicely at least explain that part. So this is actually an exercise, I should say. So this is not an example. This is an exercise taken from his book. So suppose X, so we're assuming here that X is a compact connected two-dimensional manifold, has the following, and let's call this abstract triangulation. So I'm going to write this down and I'll explain to you what I mean by that. So you have 1, 2, 3, 1, 3, 6, 2, 3, 4, 2, 4, 6, 3, 4, 5, 3, 5, 6, 4, 5, 1, 4, 1, 6, 5, 1, 2, 5, 2, 6. So the numbers are just symbols for points in X. Okay, so these are your vertices. Vertices of your triangulation. You see, these are triangles because you have 3 of them. You have 3 vertices, and 3 vertices make up a triangle. So these are just symbols. So instead of calling it, like, if you wanted to, you can call this P1, P2, P3. But the way you label it does not really make a difference. So Massey just calls them by numbers. So you have all of these numbers. These are your labels. And these labels are supposed to represent points in X. So these are some points in X. So 1 is some point in X. And 1, 2, 3, so this is supposed to represent a triangle. Again, this is an abstract triangle, something you cannot see. This is an abstract triangle that contains the vertices. Its vertices are these points 1, 2, 3. Okay, so here's what we're going to do here. So here's how you're going to get your polygonal representation. So we're going to draw a divider over here. Okay, we're going to draw a divider. So this is we're going to write over here, this is the Euclidean world you can see. And this is like the abstract space you cannot see. So all of these vertices, you see they're on this right side, you cannot see them. So 1, 2, 3, there are 3 points. But what it means is we can draw, so let's go ahead and draw 1, 2, 3. 1, 2, 3. This is a triangle. This is a triangle in the Euclidean world. Now, so what is this supposed to represent? What this is supposed to represent is I have a triangle in my abstract space, triangle that has, I mean, I'm just going to draw it like that, but you have your triangle, and there's this link between the Euclidean world and the abstract world by using this homeomorphism. So there's a homeomorphism from a standard Euclidean triangle that maps it homeomorphically to whatever that region is inside X, right? That's what this is saying. That because this is a triangulation, by definition, there's some mapping from the standard Euclidean triangle to T, which is a homeomorphism. Now this triangle, we do not care how it looks like. It does not have to necessarily contain the origin. It's just some triangle sitting inside Euclidean space. But you have a homeomorphism from this to this. Basically, you just use your affine map as before. Whatever this triangle is, so this triangle is sitting inside R2, this triangle can be mapped homeomorphically to this one, and then this one gets mapped homeomorphically to that one. So if you do the composition, you can map this one homeomorphically directly to T. Okay, so we're going to draw our pictures, we're going to draw our triangles over here, but we understand that by composing with this affine map and the triangulation maps, all of these are being mapped homeomorphically to those. But we're just going to draw the pictures over here. And we're going to be sloppy. We're going to call it 1, 2, 3. Technically, it's not 1, 2, 3. It's 3 different letters that are the ones that correspond to those 3. But to save notation and keep it simpler, we're just going to repeat the same 3 letters. So the way you do this is you pick one of these triangles and you draw it. Does not matter how you draw it. Because regardless of how you draw it, it gets mapped homeomorphically by an affine map to the standard Euclidean triangle. And then you're going to pick a triangle on the list that shares, so this is the method. You're going to have to pick something in this list that shares an edge. You see this edge 1, 3, let's say. There's exactly one triangle in the list that shares the edge 1, 3. So instead of just picking these at random, like for example 4, 1, 6, 4, 1, 6 does not share any edges with it. So you just pick one that shares an edge. So for example, 1, 3, 6, it shares an edge. You have 1 and 3, that's a common edge, and then you have 3. So, and then you have, 1, 3, 6. So you're going to draw a 6 over here, okay? And then you have 1, 3, 6 like this, 1, 3, 6. Now, notice you really have like 2 different maps. One of them is a homeomorphism like this, and one of them is a homeomorphism. So sorry about that. And one of them is a homeomorphism like this. So the reason why we're setting it up like this is because those 2 homeomorphisms will then agree at that point, because that common boundary is then mapped to the same point, right, to the same edge that those have. So that's why we're doing it like this, okay? So we have homeomorphisms on each of these pieces, and they agree right over here. So we just did this one. Then we do 2, 3, 4. 2, 3, let's draw 4 down here. So we have 2, 3, 4. So there's 2, 3, 4. Then, so that would be 2, 3, 4. We have 2, 4, 6, 2, 4, 6. So we have a 6. Now you cannot actually draw like a line going around, but that's not a problem. So here's what you do. You're going to draw 2, 4, 6, right? And this is technically a different vertex from that one, but the point is, the reason why we're doing it like this is because the homeomorphism that sends it to this one and the homeomorphism that sends that one to that one, whatever those 2 homeomorphic maps are on those 2 triangles, they will agree at these 2 points, and these 2 points have to be mapped to the same thing. That's the reason why we write it like this. So technically, this is a point in the Euclidean plane, which is different from that one. But the reason why we're labeling it 6 is this is not really the label in the Euclidean plane. This is just sort of, this point has coordinates we do not really care about, but the point that we're trying to make is whatever those coordinates are, that is the point that's being mapped to 6. So that's all that we're saying. So we have that. So we have 2, 4, 6, and we do 3, 4, 5. So 3, 4, 5. this would be, say this is 5, 3, 4, 5. So we did this one. Then we have 3, 5, 6, 3, 5, 6. So this would be 3, 5, 6. So we did this one. We have 4, 5, 1. 4, 5 is there, so we can just draw a 1 down here. So that would be 4, 5, 1. Then we have 4, 1, 6. 4, 1, 6, there it is. We can just close it up like this. So all of these are triangles, and they're all homeomorphic to the standard triangle. You can just, any affine map that does that for you, that transforms it, rescales it, will be a homeomorphism. 5, 1, 2. 5, 1, 2, 2 is over there, so we can just put a 2 right here. 5, 1, 2. And what else do we have? So we did 5, 1, 2, and we have one more, 5, 5, 2, 6. 5, 2, 6. We close it up, and this is what we get. And the point is, we have our space X, right? That's our space X. And we have these homeomorphisms. This one is being mapped somewhere. This one is being mapped somewhere. This one is being mapped somewhere. This one. So you have different homeomorphisms on different pieces in the Euclidean plane. But those pieces in the Euclidean plane, when they agree like this homeomorphism. So you see, we have a homeomorphism here, and you have a different homeomorphism here, but they intersect over there. And wherever they intersect, this is the edge that's being mapped to the intersection of these two triangles right there. Okay, so we have mappings. And we can now put an equivalence relation on this space. So this is a space in the Euclidean plane. And C, you see the 1 and the 6, they kind of have to, you have 2 and 6, and you have 2 and 6. So 2 and 6 goes like this, and 2 and 6 goes like in the opposite way. So this would mean that if we call this side A, you see, if we call this side A, right, this is A, then let's say we use the orientation going counterclockwise. This is A, so this is going backwards. So that would therefore be A inverse, right? That would be A inverse, this edge 1, 2. So I'm sorry, 2, 1. This goes in the correct orientation. So we call this, let's call this side B. Then that side would be B. And then here we have 1, 6, and here we have 1, 6. So that goes in the correct orientation. So we call this C, and we call this C. And okay, and now we can put, and now this region, this polygonal region, is mapped homeomorphically. Well, yeah, this polygonal region is mapped homeomorphically onto X. So this polygonal region is therefore mapped homeomorphically onto X, because each of the different homeomorphisms map on these smaller triangles are homeomorphisms with pieces of X. Oh, I'm sorry. I did not mean, yeah, I did not mean that. I'm not saying that this is homeomorphic to that. I meant to say that each of the triangles are homeomorphic to that. So maybe that's not what I meant to say. So then I should say that if we put a quotient topology on this polygon using the above labeling scheme, and we get a quotient space homeomorphic to X. It's going to be homeomorphic to X because all of these pieces, subpieces, are being mapped homeomorphically to X, and furthermore, they're being identified correctly with the correct points in X. So basically, you can forget about, yeah, you can just forget about the interior. Yeah, maybe I should have not done that. You can forget about, yeah, so you can just forget about the pieces on the inside. That's what you get. You see, the labeling code is therefore, in the end, the labeling code is this. It's A, B, C, A inverse B, C. That's what it is. So this is the labeling code. So X would therefore be homeomorphic to the combinatorial surface you get with this kind of labeling code, with that kind of gluing code. So that's the way you do it. That's the procedure. You can, of course, turn that into a more rigorous proof. Massey actually does provide more details to that, how you would turn that into a more rigorous proof. But I think the idea behind it is clear enough. You can actually see how it works. It's all based on the triangulation theorem. So that's kind of like the main theorem that is making this possible. And so, and then you can go on and classify what this is. So once you have a triangulation for X, you can recreate out of it a polyhedral gluing that will give you X out of it. That's basically what you do here. Okay, so this justifies why every compact connected space is a combinatorial surface. Compact connected two-dimensional manifold is a combinatorial surface. But I wanted to talk to you about something which is very much related to this, and it's called the Euler characteristic. So I have this principle, and I call it, so I made this up, it's called Euler's principle. So what is Euler's principle? It says that regardless of what area of math you learn, you will eventually come across Euler's theorem. So Euler's theorem is very ambiguous. There's lots of Euler's theorems. There's probably thousands of them. And I call this Euler's principle, that you can learn anything you want in math, eventually you get to Euler's theorem. So, and now in our topology course, to satisfy Euler's principle, we get to some Euler's theorem or Euler's formula. So this is something that I think you probably have seen before. So this is a theorem in geometry. So there's this very nice theorem, very elegant theorem, nice theorem in geometry. And it says that if you have a polyhedron, so a polyhedron is a solid body which is bounded by planes. Planes are the bounding sides. So if you have a polyhedron, then if you take the number of vertices minus the number of edges plus the number of faces, you always get the number 2. So it's a very nice theorem. I guess no one realized that before Euler, but it's very simple in the end. This is called Euler's formula. And let me just show you some pictures of it. If you have a cube, right, so here's a cube. So if you count how many vertices you have 4 vertices in front, 4 vertices in the back, so that's 8. If you count how many faces you have, so a cube has 6 faces, and if you count how many edges you have 1, so you have 4 in front, 4 in the back, so that's 8, and you have 4 more here, so that's 12. Now look at this, 8 minus 12 plus 6, what does that equal to? That's equal to 2. And you can do this with other types of surfaces. I'm sorry, not surfaces, I meant to say polyhedron. Polyhedron are surfaces, but I have to be a little bit more specific. So this is a tetrahedron, okay? So with a tetrahedron, or it does not even have to be a tetrahedron, because you might think it has to work for the platonic solids. It does not have to be a platonic solid. You can do this with a pyramid, let's say. So a pyramid is not a platonic solid because the base is a square, but the sides, the other faces are triangles. So they're not all the same. The number of vertices here is 5. The number of faces is 5. And the number of edges would be 1, 2, 3, 4, 5, 6, 7, 8. It's 8. So then you have 5 minus 8 plus 5, that's equal to 2 again. So that's Euler's formula. So you have a polyhedron, it always works. I wonder if there is an elementary way of proving it. I wonder if Euler discovered it, or whether he also found a way to prove it, because I'm not sure how you would prove it using elementary means. When the thing with geometry is some of these geometric proofs that are, especially the ones that are highly visual, the proofs are not exactly the most convincing proofs. They're way too much dependent on pictures, and there's always these what if statements, like what if it goes like that, what if it looks like that. So it's not exactly the most rigorous kind of proof. So now the way you can justify this in a way that's a lot more convincing is using topology. That's really the way you justify that. That is by far the most convincing way to justify it. And then there's no questions about it. But let's perhaps, I should say, well, so here's what we'll do. I'm going to state a topological fact, which we will be not able to prove this semester. However, the follow-up semester, if we have a continuation class, algebraic topology, we will be able to prove that later on. It's really a theorem in algebraic topology. That's the best way to prove it. So, and when we state that theorem, it will explain the classical Euler formula. So first of all, before I state the theorem, I want to give you a mnemonic how to memorize it. How do you memorize how it goes? How do you know it's V, E, and F? So the best way to memorize it is you just do it in order. 0, that's vertices, right? Vertices are 0-dimensional, edges are 1-dimensional, and faces, they're 2-dimensional. That's the way you do it. So 0, 1, 2. And actually, you can kind of push this to higher dimensions also. And it goes the same way, 0, 1, 2, 3. But we're not going to go into higher dimensions here. So we do not, we should not go there. We're only going to go up to 2, and this is the way that it goes. And here's the theorem that, first of all, I have to give you the definition. So the definition is this. So suppose X has a triangulation. So we have a topological space, and your topological space has a triangulation. And you let V be the number of vertices in the triangulation. So V depends on the triangulation. V will depend on your triangulation. Okay. You have to choose a triangulation first. After you choose a triangulation, the number of vertices that are in your triangulation, you call that V. And then you have E, which is the number of edges, and you have F, which is the number of faces. The Euler characteristic of X, and the notation we use is we use the letter chi. So this is the letter chi. So it's chi of X. So maybe instead of calling it X, how about we call it M for manifold? How about that? Otherwise, the notation looks horrible. Let's call it M. Then the Euler characteristic of M is equal to, by definition, this is how we define it. So it is inspired by Euler's formula. Euler's formula is the inspiration for this. So the Euler characteristic is then defined to be, you do it 0 dimensions, so vertices, minus 1 dimension E, and then plus 2 dimensions F. That's how you define the Euler characteristic of M. And as I alluded to, you do have an Euler characteristic for a higher dimensional manifold. So for a 3 manifold, you can do the same thing. You go 0 dimensions, then minus edges, plus faces, and then minus the 3-dimensional analog. That would be like, I guess you would simplex the number of simplices. That would be like the 3-dimensional analog. So it alternates. So it's plus minus plus minus plus minus. It alternates, and you start with the smallest dimension and you build it up. So that's called the Euler characteristic of M. And when you look at this definition is problematic. It's problematic because it depends on a triangulation. If you have a different triangulation, then the amount of vertices, edges, and faces will be different numbers. That's what's going to happen. So, but remarkably, even though the vertice, edges, and faces might be different number, this calculation of all 3 of them is an invariant that does not change. So I'm going to state a theorem, very shocking theorem, pretty amazing theorem. The Euler characteristic is a topological invariant. So it does not depend on triangulation. So you're choosing a triangulation, but the triangulation does not really matter. So you have to find the triangulation in order to compute the Euler characteristic. But in a way, yeah, so you have to find the triangulation, but once you find the triangulation, you use it to find the Euler characteristic. If you had a different triangulation, you would have gotten the same calculation in the end. It always leads to the same number. And the proof of this, so the proof of this is best done using something called homology, which is, you can say, topology part 2. So if you are interested in that, and it bothers you and you want to know why it's done, how you do it, then the way you justify this is by using something called homology. Basically, it's possible to express this number using what are known as the homology groups. So we're talking about homotopy, the first homotopy group, but there's other groups, and there's an entire collection of them called the homology groups. So you can express them using the homology groups, and once you have it, you have your calculation. So this is what we call the Euler characteristic. So it's a topological invariant. And here is the explanation for the classical Euler theorem. So let's do an example first. Let us find the Euler characteristic of the two-dimensional sphere, our favorite surface. So let's draw a polygonal representation for the sphere. We have A inverse, and this vertex and this vertex are different. They're not being identified. And yeah, so the triangulation, so how do you get a triangulation out of this? Well, I think maybe this works. So you see, this is a triangle. This vertex, and this vertex. There's three different vertices. That's the center. This is an edge. This is an edge. Maybe I should draw it like this. This is an edge. This is an edge. So the diameter. This is two edges, and that's like the third edge. Now, I know it does not look like an actual triangle, but the point is it's homeomorphic to the standard Euclidean triangle, right? You can imagine a homeomorphism, maybe using something like polar coordinates or something like that, or whatever. Well, maybe with polar coordinates you need it to be not a straight line, but you can construct a homeomorphism from this one to that one, and that's what you would have, right? So let's count the number of vertices. 1, 2, 3. So vertices is equal to 3. Okay. Let's count the number of edges that we have. 1, 2, and this is the same edge. It's the same edge. They're being glued together. 1, 2, 3. Let's find the number of faces. 1 and 2, right? We have two faces. There's two faces. So then the Euler characteristic of S2 would be equal to number of vertices minus the number of edges plus the number of faces. That's equal to the number 2. Okay? So you say, why does this matter? So here's the justification for the classical Euler formula. So here is the justification. So here is a topological justification for Euler's formula. That if you have a polyhedron, then it is homeomorphic to S2, right? A polyhedron is homeomorphic with S2. A cube, topologically, is a sphere. A pyramid is a sphere. All of these polyhedron are spheres. So polyhedrons are homeomorphic to spheres. So then it is homeomorphic to S2. And this polyhedron is almost a triangulation for S2. Now, why do we say almost? We say almost because the faces that make it up are not necessarily triangles. So if we go back to the cube, the faces are not triangles. But here's the point. You can turn it into a triangulation by cutting faces into triangles. So let's do that. On this top face, we're going to add an edge. You see, we're adding an edge. Here we're adding an edge. Here we're adding an edge, and so on. We're adding an edge for every one of the faces. And here's the main point. The number of edges, the number of faces you gain, so you're gaining faces, right? By cutting up the faces by these lines, you're getting more faces. You had 6 faces, but now because they're all got cut by 2 in half, now you have 12 faces. So the amount of faces you gain is equal to the number of edges you gain, right? A square is not triangulated, but when you triangulate it, you get the same number. And this happens with any polygon. So here's a polygon. It's not triangulated, but you can triangulate it like this, right? So notice by introducing triangles, you now have 1, 2, 3, 4, 5, 6 faces, but you also have 1, 2, 3, 4, 5, 6 edges. So the number of edges and faces that you gain is the same. So thus, V minus, so in the end it's going to go like this. So thus, the number of vertices that you have plus, so the vertices never change. So the number of vertices minus the number of edges plus what you gain, right? So it's not the original edges, it's the edges and how many you additional ones you get, minus the number of faces plus how many new faces you gain, which is the same amount, has to be equal to the Euler characteristic of the sphere. But the Euler characteristic of the sphere is equal to 2. That's what we calculated before. So that's equal to 2. And these, of course, cancel because it's the same number. And look at what you're left with. V minus E plus F is equal to 2. So that is the very, very nice derivation. So it uses triangulations, and it uses the fact that the Euler characteristic, which is defined to be this quantity, is a topological invariant. So the crucial observation is polyhedron, they're just different representations topologically of the sphere. So you triangulate the sphere in some simple way, you calculate the Euler characteristic, and then whenever you get a polyhedron, that's just a complicated way of triangulating the sphere. And in the end, the Euler characteristic does not change depending on how you calculate it. So it's a topological invariant. So let me mention a few other things involving the Euler characteristic. So the genus, so let me say this, the genus of a compact connected surface is how many holes you have. Okay, so the genus of the sphere is 0. It has no hole. I know you're going to say, but there's this empty space inside, but it's not a hole because the fundamental group is trivial. Okay, it has what you would say a two-dimensional hole. But holes here is referring to homotopy. So the genus of the sphere is 0. Then the genus of the torus is 1, because there's one hole. The genus of this would be 2, and so on. It is actually possible to define genus more generally. Not just for compact connected surfaces, but we do not need that, so I'd rather not go there. So let's not even go there. If we do not need it, let's not do it. But maybe if you're interested, you can kind of look it up. That's the genus. And then the genus of P2 would be 1. The projective plane has a hole in it. We cannot see it, but the fundamental group is, well, okay. Well, let me just say that the projective plane has one hole in it. It has a hole because the fundamental group are the integers mod 2. Now, maybe the next one we can see a little bit better. This is the genus of P2 connected sum P2. So this is, of course, the Klein bottle. And the genus of the Klein bottle is going to be 2. Maybe if I show you a picture, we can kind of see it. So let's look at this perhaps picture of the Klein bottle. Maybe we can convince ourselves with an incorrectly drawn picture because you cannot really embed it into three-dimensional space, but you can get close. This is technically called an immersion. This is an immersion. So immersion, if you're wondering what an immersion is, it is close to being a homeomorphism. Close to being a homeomorphism. You can look up the definition if you're interested, but instead of being a homeomorphism, it's sort of like it almost everywhere satisfies the properties of a homeomorphism. You can see there's some issues right where it intersects itself. So how can we see that there's two holes in it? Well, one hole, you see this opening right over here. So you can kind of imagine going through this opening and then coming around and coming back here. So you kind of get that figure 8 kind of a loop by going through it. So yeah, you kind of go in, you go through, and you go back. That would be one hole, right? That would be one hole. You cannot shrink that down to a point. But where do we get the other hole? The other loop, like the other loop that we cannot shrink, is the one that goes around this ring. It's kind of like a torus. There's this ring that goes around it. right? There's that ring that goes around it. Now, it's a little bit different from a torus because you see, a torus does not have an outside and an inside. I'm sorry, it has an outside and an inside. So you cannot draw a loop that goes like inside that hollow piece in the torus. Whereas you can do it here. You can start off on the outside, go in, come to the inside, and then back to the outside. Something you cannot do with a torus. So you have this figure 8 loop going around it, and then you also have this loop that kind of goes around this ring, something similar to a torus. So you have those like 2 different holes that one has over here. So maybe that's like a way to convince yourself why the Klein bottle should have genus 2. Okay, and then if you have 3 connected ones, right, and then the genus, if you have 3 of them, that would be 3, and so on. So that's what you call the genus. So next thing that I should mention, this is a proposition. So let M be a compact connected surface with genus G, So this proposition tells you what the Euler characteristic is. So if M is orientable, so the way we defined orientable, it means on this list. Okay, intuitively it means there's no Mobius band inside your space. To just briefly show it to you, if you go back to the Klein bottle, so here's the Klein bottle. So with the Klein bottle, this right here is your Mobius band. Or maybe we can even do it like this. This is your Mobius band. So this right over here, this is a Mobius band because point down here is being glued opposite but the point right over there. So this band over here is a Mobius band that is sitting inside your space. So if M is orientable with genus G, then the Euler characteristic of M is 2 minus 2G. That's what it is. So the sphere has genus 0, so its Euler characteristic is 2. The torus has genus 1, so the Euler characteristic of the torus would be 2 minus 2, which is 0. The 2 torus has genus 2, so then the Euler characteristic would be negative 2. So in particular, if it's orientable, the Euler characteristic has to be an even number. If M is non-orientable with genus G, then the Euler characteristic would be 2 minus G. So this one could be an odd number. So in particular, the only surface with Euler characteristic 2 is the sphere, because G cannot be 0 here. When you talk about non-orientable surfaces, the genus has to be at least 1. Okay, so this is the proposition. How do you prove it? This is actually very easy. So proof, this is an exercise. You can prove this. How do you prove it? You just use triangulations. We've shown how to triangulate a torus. So if you have a double torus, it's basically the same triangulation, just repeated twice. Basically, that's what it is. So you will notice that when you talk about orientable surfaces, there's a 2G, and when you talk about non-orientable surfaces, that is a G. That does make sense because the torus has 2 pairs of symbols, whereas non-orientable surfaces, they have just 1 pair of symbols. So that's kind of maybe explains why it goes like this. But you should be able to prove this yourself. This is not difficult. It's just a computation. You just have to take your polygonal representation for M and go ahead and triangulate this. Now, I also want to say this, that we can use, so let's also say this, so we can use Euler's characteristic plus orientability to easily classify a surface from either its labeling, its proper labeling scheme, or even its triangulation. So without using copy and paste. So copy and paste is tedious. Now the reason why we talked about copy and paste is because the classification theorem for combinatorial surfaces was explained using copy and paste. All of those formulas that we mentioned above, the formulas for the Euler characteristic of different surfaces, that assumes the classification theorem. It assumes that you know that is your complete list. So once you have the classification theorem and you know what the different kinds of surfaces are, then you can assert what the Euler characteristic is. So it would be circular if you avoid it's kind of like you use copy and paste to prove something, but when you have to actually classify a surface, you do not use it. You kind of just use the Euler characteristic. So let me give you an example. This is the example that we did last time. So here's the example. I'm going to show you how this works, and you'll see how nice this is. So this is the example. So let's say the proper labeling scheme is denoted by A, B, C, D. A, B, C, D. Okay, so that's the proper labeling scheme. So let's draw a picture for this. So this is A, B, C, D. A, B, C, D, like this. And we remarked that this really is, all of this is really the same thing as all of that together. So if you call this E, this is E, and this is like E squared. So this represents really the projective, it's the projective plane in disguise. And you might easily make a mistake because you have 8 sides, so you think that it's a more complicated surface. But if you use copy and paste here, we saw that this thing actually greatly simplifies, and in the end, you're left with the projective plane. So we have to use the Euler characteristic and orientability. So let's calculate the Euler characteristic. Let's find how many vertices we have. So we begin with this vertex right over here. That's our vertex. Okay. So this A would correspond to this one right over there. Okay, so these correspond. This A will correspond to that one. Okay. And then this B corresponds to that B. We have a D over here. These correspond together. So these are actually different. They do not get glued together. And then this one for B only gets glued with that one and nothing else. And then this is the one that's left over, gets glued with that one. So unlike the other examples where all 8 vertices or 10 vertices get identified to a single point, here that does not happen. So the number of vertices is equal to 4. Let's actually, no, that's wrong. I did not even create a triangulation yet. So let's create a triangulation. So to create a triangulation, you can pick the point in the middle and just draw triangles. That's all you have to do. So let's count how many we have. 1, 2, 3, 4, 5, 6, 7, 8. Right? So let's count this again. How many vertices? We have 1, 2, 3, 4. These are copied. They're the same vertex in the triangulation. And then this point in the middle, that's an additional one. So that would be 5. The amount of edges, how many edges do we have? Well, the A's get glued together. So it's A, B, C, D. So we have 4 edges. How many faces? Faces, we have 1, 2, 3, 4, 5, 6, 7, 8. None of them are glued together. So we have 8 of them. So we go ahead and we find the Euler characteristic. So the Euler characteristic here would be equal to, it would be equal to 5 minus 4 plus 8. Oh, I made a mistake with the edges. I just realized, big mistake with the edges. So it's 4 edges, but I forgot to count 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I forgot to add in another 8 of them. So this is 12. 5 minus 12 plus 8. This is equal to 1. So the Euler characteristic is equal to 1. And then you have to determine, is it orientable or not? So this is going to be equal to either 2 minus 2g, or it's equal to 2 minus g. So which one of these is it? So if the genus of this surface was G, then the Euler characteristic based on that formula would be equal to one of these two. But which one is it? Now, you're going to tell me, of course, it has to be the second one, because this one's always an even number, and that's an odd number. You would be correct. But I do want to address the issue of orientability. How can you tell if it's orientable? It's actually very easy to check if your surface is orientable. You just look for a twisted pair. So for example, you look for AA or BB, right? Do you have a twist? That's what we call a twisted pair, because when you glue it, you do a twist. Do we have AA? Yes, we have lots of twisted pairs. If you have at least one twisted pair, oh, I'm sorry, if the surface is non-orientable. To check if a surface is non-orientable, you just look for a twisted pair. So you found the twisted pair, and so your surface is not orientable. And it kind of justifies, so let me kind of maybe draw the picture again for why you would say this is not orientable. Because these are being glued opposite of each other, this would mean that if you were to take this piece, let's say this piece, and you draw this band, so that would be a band going between those two, so that would be your band. When you glue the edges of this band, they get twisted. That's why we call it a twisted pair. And by twisting it, there's a Mobius, you've just produced a Mobius band. So there's a Mobius band that sits inside your space. You can also draw a Mobius band like that. So there's a Mobius band that's sitting inside your space. So because of that, that should give you an indication that it's not orientable. So therefore, the correct one you have to use is this, and then you solve for G. So G is equal to 1, and so your surface is the surface P2. And you just determined what the surface is without using any copy and paste. You just looked at your polygon, you counted vertices, edges, and faces in a triangulation. You determined by looking at it whether it is orientable or not, and that was enough information for you to figure all of this out. So I want to finish with one more thing. So let's just finish with this. So we can use, so recall what we said. So if S1 and S2 are proper labeling schemes, that are disjoint. Well, let me change this. Definition. Let X and Y be two combinatorial surfaces. So we're going to choose proper labeling schemes S1 and S2, which are disjoint. They have no common letters. And X, and the quotient that you get out of S1 is X, and the quotient you get out of S2 is Y. So we define X connected sum Y as the combinatorial surface that you get from just juxtaposing these two words together. So this is the way we define the connected sum. We mentioned during lecture that there is a way to define the connected sum in general between manifolds, but then there's complications that arise. So the way we did it is we defined the connected sum combinatorially, where you just choose a combinatorial structure to represent X, and you choose another one to represent Y, and then you define the connected sum of two such surfaces to be the surface obtained by just putting the two words right next to each other. So that's really the way we defined it. Now the problem with this kind of definition is, how do we know it is well defined? So the question that we asked in class, is this well defined? So would this be well defined? So yes, this is going to be well defined. The way you can show it, the easiest way to show this is, so since we have classification and the Euler characteristic, so since we have both of them, we can compute the Euler characteristic of this and the Euler characteristic of this. So basically we're saying, let's say you replace it by a different labeling scheme, and you replace this by a different labeling scheme. So this gets replaced by S1 prime, S2 prime. How do you know that the topological space you get in the end is going to be homeomorphic to that? And so this is like a well-defined operation. So it basically just comes down to the classification theorem. You have a classification theorem, so you know whatever So whichever one this is, it has to be like a connected sum of planes, projective planes or tori. And then you can also use the Euler characteristic to compute this. So I think that maybe this would be an appropriate question to put on your homework. Yeah, this would be like an appropriate question to put on your homework, and you can try to figure it out. So you can show it's well defined by kind of taking advantage of the Euler characteristic. So we'll finish here. This is our discussion. This completes our discussion on surfaces. Next time we'll talk about graphs and how they get embedded in surfaces, because there's actually another Euler's theorem which is very similar to the one that we mentioned today, and that's the Euler theorem for planar graphs. If you ever seen that one in a graph theory course. So if you ever seen that one and you wonder what the relationship is with the other Euler theorem, we'll show the connection and we'll actually give generalizations beyond planar graphs. So we'll finish here.